Hello everyone, welcome to the video. Today we are going to solve the problem 01 knapsack problem. In this problem, we are given n items and every item carries some value. Every item also carries some weight. So for all the n items, we are given the value that it carries and the weight that it carries. Now our job is to pick some of these items and put them in a knapsack. But we want to pick the items in a way that we maximize the value that we have picked. But there is a constraint. The constraint is in terms of the capacity of the weight that the knapsack can carry. So, this is the problem that we have a fixed capacity that the knapsack can carry. We have n items with their values and weights. We have to return what is the maximum value that we can put in the knapsack within this capacity. We are going to solve this problem today. We will go through the thinking process, we will write the algorithm, and then we will also see a working code for the same algorithm. Later, we will also see an extension to the problem. The extension being that we have to also return the items that we have picked and not just the maximum value that can be achieved. So before we start, if you are new to this channel, please don't forget to subscribe and press the bell icon. Let's start. To begin with, let us first note down the key things given in the question. We are given that there are n items. Each item carries some weight and each item carries some value. The weights and values of these items are given to us in terms of array. Now what we have to do, we have to put some of these items in a knapsack. But there is a constraint. The knapsack has a limited capacity of W in terms of weight. So we cannot exceed this capacity when we put some of these items in the knapsack. So what do we have to do? We have to return what is the maximum total value that we can make in the knapsack under this capacity. So if we consider an example, we have 3 items. Each of them has weight 1, 1 and 1. But the value of each of them is different, 10, 20 and 30. Now in this case, if our capacity is 2, what is the maximum value that we can make? We can make 50 by picking up these 2 items, one with value 30 and one with value 20. So if we consider our solution as a black box, we are getting as input what are our number of items, their values, their weights and the capacity of the knapsack. And what do we have to return? We have to return the maximum value that we can form. So what will our function signature look like? Our function signature will look something like this. Let's start thinking about this problem. So our aim is to get the maximum value. Now, what is the first thought that comes to our mind? The first thought that comes to our mind is that we should start picking up the items which have the maximum value. So we pick 30 and we pick 20. Now this works in this example, but it is not guaranteed to work in all examples. Consider this example. In this example, we have 3 items, but their values are 10, 20 and 25. And the weights are 1, 1 and 2. The capacity is 2. Now if we go by this thought process, we will first pick 25 and then our capacity would have exhausted. So our maximum value that we would have returned would be 25. But that's not correct, right? We could have picked 10 and 20. We would still be under our capacity and the maximum value that we could have made was 30. Therefore, this approach is not always guaranteed to work. Another thought that could have come to mind is that we start picking up items with least weight. So what will happen is that we will get to pick more items. So probably value will be maximized. But it is easy to say that this thought is also very flawed. In this example, if instead of 25 we had 40, then we would have this thought process would not have worked because we would have picked 10 and 20 and rather we should have picked only 40. So we can say that this approach is also flawed. Then another thought that could have come to mind is that we try out all possibilities. We try out all combinations of which items we pick and which items we do not pick. And then for each of those combinations, we see that what is the value, what is the maximum value. Then finally, out of all the possibilities, the possibility that gives us the maximum value, the items, the combination of items that gives us the maximum value is what we desire. So we can return that maximum value. This approach will work, but we can see that as the number of items grow, the number of possibilities or the number of combinations of which item to pick and which item to not pick will grow huge. So this option is very expensive. Since we can't think of any other straightforward way to solve this problem, let's see if we can solve this problem using recursion. That means from our original problem, we will have to identify a smaller problem, and we'll have to see if we can use the answers to that smaller problem to derive the answer for our original problem. So how do we first identify the smaller problem? What are our inputs? Our inputs are the number of items and the capacity of the knapsack. So if our inputs get reduced, our problem gets smaller. So let us try to reduce the number of items first. Let us say we are dealing with only first two items. This encircled part is our current problem. Now our capacity is still 2. Now if somebody comes and tells us the answer to this smaller problem, let's say m, then can we use this m and the value and the weight of the last item? Can we use these three to derive the answer for our original problem? No, we won't be able to, because the answer for our original problem would also depend on what are the items that we picked here. Maybe for the answer to our original problem, we may have to drop a few items from this and pick this item. So we never know. So we can say that the simple recursion, direct recursion on this problem is not very straightforward. Even we had reduced only the second input, even if we had reduced the capacity and had kept all three items intact, even then it would be very difficult for us to figure out the answer to our original problem from the answer to the reduced capacity problem. So simple recursion is not straightforward, and we need to think of something else. We will need to make a few more observations about the problem. Consider the solution case. What do I mean by solution case? Consider the case where we pick items in such a way that we get the maximum value. Now for any general example, in that case, we would have picked some of the items and we would have not picked some of the items. Let us say that if there were 5 items, we picked all those that are marked with right and we did not pick all those that are marked with cross. Looking at this, we can definitely say one thing, that whatever be our solution for any example, we can say one thing about that solution. That solution will either contain the last item or it won't contain the last item. This is a fair statement to make. From this, we can say that the answer that we are looking for, the maximum value possible, we can derive it in the following manner. We calculate the maximum value possible for the case where we include the last item, and we calculate the maximum value possible for the case where we exclude the last item. Now, the maximum of the two will be our answer. So, we can say that max val that we are looking for is maximum of the include answer and the exclude answer. Include answer meaning we have picked the last item, and exclude answer meaning we have not picked the last item. Now let's understand the include case a bit more in depth. So let's say that we are including the last item. So let's say in this example, we are including the third item whose value is 30 and whose weight is 1. So we already know what will be the last element's weight and last element's value. Now our aim is to find what is the answer for this include case. If we are including the last item, what is the maximum value that we can form? So in this example, if we have already included 30, that means we have already achieved the value 30, but we have also included the weight 1 and our capacity was just 2. So now what does our remaining problem mean? Our remaining problem is that from the remaining two items, we maximize our value, but now our reduced capacity is 2 minus 1, 1. So our remaining problem is that out of these two items, we maximize the value with capacity equal to 1. So if we are representing our original problem as knapsack of I and j, where I is the number of items and j is the capacity that we have of the knapsack, what is the answer for this include case? Its answer is the value of last element, since we are including it, plus knapsack of I minus 1 comma j minus last element weight. Why do we say that? Because we have already included the last element, so now we have to maximize the value using the remaining elements, and our capacity is also reduced by the weight of the last element. This is a fair statement to make. So this is nothing but just a similar problem with reduced inputs. That means we can solve this problem using recursion. Now let us consider the exclude case. In this case, we are sure that we will not include the last item in our solution. So let us see what is the maximum value that we can make when we have this constraint that we won't pick the last item at all. In this example, now when we say that we won't pick this third item at all, what is our problem? Our problem that remains is that we have to use only these two items and we have to maximize the value, and our capacity is still 2. If we say that we are considering first I items in our original problem, then what are the items that we are considering in our sub problem? We are considering first I minus 1 items, as we are sure that we are not including the last item. Similarly, if the capacity was j in our original problem, what is the capacity for our sub problem? Our capacity is still j because we have not included any item. With this, how can we express the answer for exclude case in terms of our sub problem? We can say that knapsack of I and j for exclude case will equal to knapsack of I minus 1 comma j, because we have to solve using I minus 1 items and our capacity is still j. So our final answer, the maximum value that we can achieve using these items and the capacity, will be equal to the maximum of these two answers. The first answer denotes the answer for the include case. It says the maximum value that can be achieved using these items, but we have to include the last item. And the second says the maximum value that we can achieve using these items, but we have to exclude the last item. So the maximum of the two is our final answer. Now this is also our recursive relation, as we have expressed our original problem in terms of smaller problems, and we are using the answers of smaller problems to derive the answer for our original problem. So now we have this recursive relation, so we can try converting this into algorithm. As with any recursion problem, we will solve this step by step. We have already done the first two steps. We have identified the recursive relation. The recursive relation says that the maximum value that we can achieve by using the first I items with capacity of knapsack being j is equal to the maximum of the include answer and the exclude answer. And we have calculated the include answer and exclude answer in terms of the answers to smaller problems. We have already also identified the inputs to the recursive relation. These inputs will go into our recursive method, knapsack util. In this method, as per the recursive relation, I and j are the inputs. I denotes the first I items that are being considered. J denotes the capacity that is being considered. But we can see we will also need the last element's value and last element's weight. So we will have to pass the weight and value array as well. And this will return the maximum value that can be formed in these constraints. We will initially call this method with I is equal to n, whatever is the number of items given, and j is equal to w, whatever is the capacity of the knapsack given. Let us now try to convert this recursive relation into our algorithm here. First of all, let's calculate what will be the value for last element val and last element weight. How do we calculate this? Now, if we are considering first I items, then at what index will the last element lie? The last element will lie at I minus 1th index. So, our last element value is equal to val I minus 1 and last element weight is equal to weight I minus 1. Now, our first step is to find the answer for the include case. But the include case makes sense only when the capacity is greater than the weight for the last element. So we add this condition. Now, if this condition is satisfied, what will be the answer for our include case? As per this recursive relation, the answer for include case will equal to the value of the last element plus the maximum value that we can achieve by using only first I minus 1 elements and with the reduced capacity of j minus the weight of the last element. So this is a call to the same method. This is a recursive call to the same method with reduced inputs. So this way we can get our include answer. But this is only for the case when this condition is satisfied. If the weight of the last element is greater than the capacity, then it does not make sense to include the element. So in that case, we can say the maximum value achieved by include case is 0. So we write here that include answer is 0 in the else case. Now exclude answer will be simple as well. If we are not including the last item at all, then our problem is to maximize the value using first I minus 1 items with the same capacity j. So we call this recursive method with these inputs and we get our exclude answer. Then our current answer is nothing but maximum of these two. So we get our current answer and we return it. So this will be conversion of our recursive relation into our algorithm. But is this algorithm complete? No, this is not complete because this will keep going into infinite recursion as this same method will keep on calling itself and it will never terminate. So to terminate that, we need to something called as base or terminating condition. And when do we achieve base or terminating condition of a recursion? We achieve that when our inputs are smallest. And when our inputs are smallest, in our case, the inputs are I, the number of items, and j, the capacity. So when, let us say, when do our number of items become smallest? When I becomes 0. What does I become 0 signify? It means that there are no items to consider. So obviously the maximum value that we can achieve is 0. Now let us see what is the minimum value that j can reach. Now j is getting reduced by a random number, random weight in every recursive call. But we are making sure that we are reducing j by the random weight only if j is greater than that last element weight. So at max, j can also reach 0. Now what does j is equal to 0 signify? That means our capacity of knapsack is 0. And that means the maximum value that we can make is 0. Now this algorithm is complete, but it has very high time complexity. Why do we say that? Because there are a lot of overlapping problems here. How do we say that? Let us say we are dealing with this example where the weights of the three items are 1, 1 and 1 and values are 10, 20 and 30. So initially we will have to solve for I is equal to 3 and j is equal to 2. Now let's see, as the recursion progresses as per this recursive relation, how does the recursion tree look like. Now, from here, if we consider the include case first, then for this, as per this recursive relation, we will have to solve for I is equal to 2 and j is equal to 1, since the weight of the last element is 1. And if we do not include the last element, then we have to solve for I is equal to 2 and weight is equal to 2. The capacity remains the same. Similarly, we can grow the recursion tree further. Now what can we see here? We can see that we have same problem, same inputs that we encountered twice in this recursion tree. What does that mean? This means that for the same input I is equal to 1 and j is equal to 1, we would be solving twice. This is not good, right? This is inefficient. And here input was very small. If the inputs were very large, then we would see a lot of many overlapping problems. And every such overlapping problem would be overlapped multiple number of times. And this would lead to gross computational inefficiency. So how do we solve this problem? We can do one thing. Whenever we encounter an input, we solve for it and we store its result somewhere. The next time, whenever we encounter the same input, we won't have to solve for it again. We will go into our storage and return the result directly from there. So this way, we can solve this problem of overlapping problems. But how do we do that? We first need a way to store the information that for a combination of I and j, this is our answer. What data structure can we use here? We can use a map. Why map? Because if we want to look for a value against a key, map can return that in the smallest time, the constant time. But with map, we also need to define the data types of key and value. The value is easy because our answer is nothing but the maximum value that we can form, which is integer. So our value will be of integer type. What should be the data type of our key? Our key should be uniquely able to represent the combination of I and j. We can do that using string. We can simply add an underscore between I and j and form a string. This string will uniquely correspond to a combination of I and j. Therefore, our key can be of the data type string. Okay, so now we have this map and we know how to solve this problem. So let us see how does having this map change our algorithm. Now we have a new parameter into this method. So wherever we are calling this method, we will add this new parameter as well. This map is of type string, integer. Our key is a string data type. So we will have to build our key using I and j somewhere. And now, before returning our answer, we will save this answer in the map against the key. And before calculating the answer for any input, we will first check if this key or if this input was already seen. If this was already seen, then this would have been present in the map and we can return the answer directly from the map. This way we avoid the duplicate calculation. And now this completes our algorithm for top-down dynamic programming approach. Now what will be the time complexity for this algorithm? The time complexity will be of the order of n into w. Why? Because for every combination of n and w, we are calculating the answer once. And similarly, space complexity will also be equal to big O of n into w because we are storing the results for these many combinations. Let us now see a working code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our main method. It takes as input the number of items, the capacity of the knapsack, and the values and the weights of those items. And it is supposed to return the maximum value we can take in the knapsack against this capacity. So first of all, we declare a map to store the results for a combination of I and j. This map is of data type string and integer. Then we call our recursive method. We call our recursive method with initial values of I and j as n and w. We also pass to it the weight value array and the map that we have just declared. Now let us see what does our recursive method look like. In the recursive method, first of all, we check the base conditions. Our first base condition is when I is equal to 0. I is equal to 0 means there are no items to pick. That means the maximum value that we can carry is 0. The second base condition is when j is equal to 0. J is equal to 0 means that there is no capacity left in the knapsack. In that case, the maximum value that we can take is 0. So we put 0 here. Then to deal with map, we need to build key. Our key is something like this I underscore j. So we use this simple method to build the key. Then we check if we have already seen this input. So we check that whether it is present in the map or not. If it is, then we return the answer directly from the map. If it is not present in the map, that means we are seeing this input for the first time. So we have to calculate the result for it. To calculate the result for it, as per the recursive relation, we will need these two values, the last element's weight and the last element's value. Now if we are considering first I items, then the last element lies at index I minus 1. So we get the last element weight as weight I minus 1 and last element value as value I minus 1. Now our aim is to get the answer for the include case. Include case meaning that we include the last item. But including the last item makes sense only if our capacity is greater than or equal to the weight of the last item. Therefore, we add this condition. Now let's say this condition is satisfied. Then what will be answer for our include case? Since we have already included the last element val will be part of the value that we can achieve. So we add this. And now we have to find the maximum value that we can achieve by using remaining I minus 1 items and with the remaining capacity of j minus the weight of the last element. So we call this method recursively to find the answer for this. And this way we can get the include answer. And if this condition was not satisfied, that means our capacity was lesser than the weight of the last element, then there is no point in including the last element. So our include answer will be equal to 0. Now let us come to the exclude case. For exclude case, we are sure that we won't include the last item at all. That means we have to find the maximum value that we can achieve using first I minus 1 items and with the same capacity j. So we call this method recursively using these inputs to find the answer for the exclude case. Now our final answer for I comma j will be maximum of the include answer and the exclude answer. So we can return this, but before returning this, we put this answer in our map so that if we get the same input again, we can directly return it from the map. So this completes the code for our top-down dynamic programming approach to 01 knapsack problem. Let us now see our code in action. We are giving it one test case. The number of items is 3. The capacity is 2. The values of the number of items is 10, 20 and 30 and the weights of the 3 items are 1, 1 and 1. Let us see what is the answer that it throws up for the maximum value that we can achieve. It throws up 50. 50 can be achieved by picking the last 2 items whose values are 20 and 30. So far, we have been focused on finding the maximum value that can be obtained in the knapsack. But there could also be an extension to the problem. Instead of just returning the maximum value, someone could ask us to return the items that should be picked in the knapsack to obtain the maximum value. For example, in this example, the items are at index 1 and index 2. 20 and 30 values make up the maximum value 50. How do we solve that? Let's see if it is possible to extend our algorithm to derive that. In the algorithm, we first calculate the include answer and then we calculate the exclude answer. But we choose only one among the two, and we choose the one with whose value is maximum. That means at this stage, for I and j combination, we know whether we should include the last element or we should not include the last element. Now this gives us a hint that it is probably possible to trace the items that were included in the knapsack. Let us say we somewhere store this information that for a pair of I and j, whether we included the last item or we did not include the last item. What data structure can we use to store this information? We can simply use a map of string and integer, just like the map that we used to store the results for every pair of I and j. Let us say that while going through the previous algorithm, we filled these two maps, the results map and this include exclude map. What does this mean? That if we are considering first three items and our capacity is 2, then the maximum value that we can obtain is 50. If we are considering the first two items and our capacity is 1, then the maximum value that we can obtain is 20. If we are considering first item and our capacity is 0, then the maximum value that we can obtain is 0. And what does this map denote? That means if we are considering first three items and our capacity is 2, then to obtain this maximum value, we need to include the third item. Which is the third item? This, whose value is 30. Similarly, if we are considering first two items and if our capacity is 1 and we have to obtain the maximum value, then we have to include the last item, the second item, which is 20. Now, our aim is to figure out the index of the items that were put in the knapsack to obtain the maximum value for n is equal to 3 and w is equal to 2. For 3, 2, we have to obtain what were the items. Now, can we use these two maps to obtain this? Let us see. We start from 3, 2. When we are at 3, 2, we know that to obtain maximum value 50, we have to include the last item. The last item means the third item, whose index is 2. So we store this index somewhere. So we have stored 2 here. Now, since we have included the last item, our next problem is I minus 1. That means 3 minus 1, 2. And j minus last element's weight. That means 2 minus 1, 1. So our next problem is 2, 1. Now for 2, 1, to obtain the maximum value, we know that we have to include the last item. What is the last item here? The second item. So that means we have included the item at index 1 as well. So we will note this as well. So we have noted that we have now included 1 as well. Now since we have included 1, now our sub-problem becomes 2 minus 1, 1, comma, this j was 1 minus the weight of last element, which was also 1, equal to 0. So our next problem becomes 1, 0. Now for 1, 0, we know that it is not possible to make any value. That means now we don't need to go and explore further to see what more elements were picked. These two elements would do. So we can see that we can use the two maps to derive what are the items that we included in the knapsack. Let us now try to formalize our thoughts into an algorithm. Clearly, we are iterating. But we are iterating till when? We are iterating till this max value is greater than 0. And what all do we have in every iteration? We have I, we have j, and if we have I and j, we have what is the maximum value that we can obtain for this I and j through this results map. Since we have I, that means we also know the last element, we know the value of the last element, we know the weight of the last element. And we also know whether the last element was included or excluded through this map. Now, what do we do in every iteration? We first check if that element was included from this map. Checking whether the last item was included or not is simple. For the same I and j, we will just check if the value is 1 or 0. Now, let us say if this item was included. If this was included, then we have to note the index of the last item. So we push the index of the last item in the stack. We are here using stack because we are getting the information about the later elements first. Now, if we have included the last item, then through this recursive relation, we know what is our next problem to go to. So we can update our I and our j accordingly. So we update our I and j here. And if the last item was excluded, that means there is no item to be pushed into the stack right now. Therefore, we only update I and j as per this recursive relation. We go on iterating till the max value is greater than 0. Once the max value is equal to 0, that means there are no further items that we need to include. At the end of all of these iterations in the stack, we will have indices of the elements that were put in the knapsack. We can simply convert this stack into a list and return. This way, we have a way to return the actual items put in the knapsack to obtain the maximum value. The only thing that now remains is filling up of this map. Filling up of that map is easy, as here we can just check what is maximum, the include answer or the exclude answer. If the include answer is maximum, we will put the value in the map as 1. And if the exclude answer was maximum, then we would put the value in the map as 0. So this is how we can solve this problem of returning the items.
This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also, let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.